Can you see my screen?
Mm, not yet. Yes, yes, I can see your screen now.
All right. Okay. So we're going to look at this, and I'm just going to take it again from the start so that it's clear to you. Very quickly, I think Faith already gave a walkthrough. She already gave the definition of the database, an organized collection of data that is stored electronically. In our case, what we're going to be studying here is going to be stored electronically. And then it doesn't rule out the fact that there are people who have non-electronic databases, right? Like maybe having a ledger with some information inside, as Faith mentioned yesterday. Okay, so databases, unlike the books that people have, the registers, the spreadsheets, and so on, they can handle large amounts of data, and they allow multiple users to be able to access it at the same time. Now, you may also be thinking, okay, but this is something which is common across spreadsheets, maybe even across a text file. What else? Even across the physical ledger, true, because it's a database. But then these electronic databases have something else. They provide an extra layer of security, consistency, and reliability. So, an example of content that, by the way, feel free to stop me at any time if you have a question.
Okay.
So, an example of content that can be stored in a database, take for example, a student database is this. So, you have a student with all their information name, course, grades, matricle number, student ID, address, and so on and so forth. No. And yesterday, I mentioned to her that we can't talk about databases without even talking about data, without understanding data. And then she mentions to you that data are the raw facts and figures, right, or observations which have not yet been processed. That's why they are called raw in its. And I'm going to use the same word in its. Let me say in its purest form or in its rawest form, rawest state. That is data. Now, data has its life cycle, just like a human being has their life cycle, right? People are
Yes.
born up to the point where they die. So, in a similar manner, data is created up to the point where it is destroyed. And there's so many things that happen in between. So, at the bottom, you're going to see these additional resources, and they're put here so that you can go through it. So, inside it, one of it is the data life cycle, and you can read extensively about it, right? So you're saying when the data is generated, okay, like now you and I are having a conversation. This is data that we are creating, right? The site you visit, when you visit all of these websites, when you want to check your browsing history, that is data that you have created, right? But all of that data is actually meaningless until something is done on it, transforming it to information, which as a result gives us knowledge or insight in order to guide decision making. So this is the entire life cycle which you can go through. All right. She also mentioned the categorizations of data, right? So
Yes.
data can be categorized by nature and by structure. So by nature, you have two types, quantitative and qualitative data. So qualitative data being data that talks about characteristics, what you describe, right? And then quantitative, like when they tell you the quality of something, like your friend can ask you, bro, how is the quality of this phone or this place and so on, and you'll be like, it's nice, it's not nice, they have this and that you're describing. So qualitative characteristics. But then when you come to quantitative, you're now talking about numbers, figures, measurement. Can you count it? Quantity, right? How many is this? It is five. How many is that? 11.5. What is the measurement? 3.7, and so on and so forth. All right, so that's the difference between qualitative and quantitative data, and this is how data can be categorized by nature. So for quantitative data, you have two types, can further be divided into two types. You have discrete and you have continuous. So discrete, meaning that it is fixed. Just think of discrete data like an integer. Integers are positive or negative whole numbers, right? So they are not fractions, there are no decimal points. That is what discrete data is. For example, your age. How old are you? You're maybe 21, for example. That is discrete data. How many students are there in class? There are 5 students in class, and there are 20 students in class. It's not possible for 20.5 students to be in class, right? Or
Yes.
11.3 students to be in class. But then when it comes to continuous data, this is what, now think of it now as decimals, floating point numbers. So decimals or floats, as you call them mostly in programming, these are numbers. They are positive or negative numbers. Now, these numbers, okay, like I said, they're decimals, right? So you can have like 11.3, negative 1.5, negative 1.0, and so on and so forth. So, what are some things that you could describe with decimals like this? An example is temperature, an example is money, right? To pay for this service is maybe $10.99. All right. But then for um, qualitative, you have two types also. So remember, qualitative is the description, the characteristics, right? You have two types also. You have nominal and ordinal. So with nominal data, um, this is data that has no inherent form of order or ranking or categorization. Okay, take for example colors, right? Is an example. This thing is green, this house is white, and so on. What else? Gender, he is male, she is female, right? But then with ordinal, I mean, even from the name ordinal, order, it has a way that it can be ranked. While it is descriptive, it can be ranked. Okay, take for example, you want to describe the level of something. So you can either say low, medium, or high. You see that you're ranking, but you're still describing, right? But
Yes.
nominal, you cannot say that maybe someone is more male than another person or more female than another person. So that is just the difference. This overview, well, all of this info and data was actually for the data guys, but then it was just good that you guys understand it also. All right, but then we've talked about data, categorizing data by nature. Now, what about by structure? So, by structure, it can be further categorized into two types, into three types. Sorry. The first one is structured data. The second is unstructured, and then the third is semi-structured. Sorry, I'm just trying to get this so that it can serve as a reference also. All right. So structured data, this is it, so you can just follow. Structured data is organized into rows and columns. So rows are horizontal and columns are vertical, right? So typically they fit into a tabular form. So a spreadsheet, I don't know if you have an idea of databases already, but a database, a relational database rather, is an example of how it's an example of structured data, basically. Okay, but then unstructured data, it does not have any fixed form. It doesn't have any fixed format. Take for example, text documents, images, videos, audio recordings, social media posts. It has no format. But then with semi-structured data, from the name, you see that it falls in the middle. So it's actually in between structured data and unstructured data, right? So semi-structured data is not strictly tabular per se, although it has some structure. It is flexible, and a good example of this is JSON. So JSON, as you mentioned, stands for JavaScript Object Notation. and it's just a way of representing data, representing information. So take for example, this is an example of some JSON data, right? So you can have some information about a patient. So you have their patient ID, just like you have a matrix for a student, right? What uniquely identifies that patient? Because patients could have the same name, same age, same address, and so on. Their age, 45, maybe what they've been diagnosed of, malaria, right? So this is how JSON actually looks like. Let me see if I can pull up some other examples for you. Oh, let me see what this guy gave. All right, this is nice. So this one is actually straightforward. Okay, and you said you guys ended in key value databases. So what?
Database. Yeah.
Yes. So what you're talking about is JSON, which is an example of semi-structured data, right? And it is stored in this format: key and value, key and value. That's why they call it a key value pair. Is it clear?
Yes.
All right. So take this example. Who is this? A human being. They have their ID, their name, and their email. If it was in a table, right, you're going to have rows and columns, right? This would be the ID column, the name column, the email column, and then all of this is going to fit. All of this is going to fit inside it. Let me see if I can get an example for you. Okay, nice. So if we were to fit this on a table, how is it going to look like? For our columns, we're going to have ID, right? We're going to
Yes.
have name, and we're going to have email. And all of this information is going to go under 101 Alice. What else? Alice at example.com. And if there were more students, please give me a minute, love it.
Okay.
Sorry, I had to attend to something. Where were we? We're looking. Are you guys there? Love it.
Yes.
Daniela, Jim. Okay. So let me see. I was trying to give you this example of JSON data and how it can be represented in a tabular structure, right? So this can easily be put in a tabular structure. And you see that on its own, as JSON, it actually has some format. Now let's look at this one, which is actually nested. Nested meaning that, okay, within this JSON payload, this is called a payload, within this JSON payload, there's actually more data that is nested inside it, like what we have here. Okay, so let's say that um, for a particular customer database, right, we want to record the customer's order. So hence there'll be an order ID. We'll come to all of this. But just know that for every row in a table, in a database, there must be an ID that uniquely identifies that row. Just like for you guys now, your students. Imagine that some of you had the same name, the same information all through. What is going to uniquely identify you is your student ID. You guys have, like you see, some of you have SAF and then some numbers, others have DAF and then some numbers. All right. So if we're to represent this information here on a table or in a tabular structure, how is it going to look like? I think this, to an extent, is actually achievable. But then, what about this? It starts getting more and more complicated. There's a lot of nesting and nesting and nesting. How are you really going to put it in a table? Because this represents one column, right? This is another column. But these are other columns also that are related to this one itself, and so on. Are you seeing? All of this is under this. So it just keeps getting, well, not complicated, but for lack of a better word, I'm going to say complicated. It just keeps getting complicated. But then that's just the whole idea on JSON. It is semi-structured data. Another example of semi-structured data is Excel. So for the software guys, those of you who are going to be on the back end, Excel data. So, all right, those of you who are going to be on the back end in due time, you're going to realize that all the responses that you're sending to the front end, for the front end guys to consume or for the mobile guys to consume, are going to be in JSON format, right? At first, XML used to be used, but then it's no longer as widely used as JSON. JSON has taken over, if I should put it like that. So if any of you are familiar with HTML, if you're not, it's okay. We're going to see it as we progress in future. But then if you're familiar with HTML, you see that it has this XML data has this nature of storing content in using tags. These things are called tags. So this is, let's say, the collection ID opening tag and the collection ID closing tag. It has the information. What else? Source item key tag has the information. Title has the information, and so on and so forth. I'm sure you can already start picturing how this would look like if you were JSON or if you were in a table. So it has some structure, but then it's not entirely structured. That's why it's referred to as semi-structured data. All right. So back to the notes on databases. So after talking about databases, we should also look at database management systems. And database management systems is the software that allows you to interact with your database or interact with the data in your database. So with database management systems, you're able to create, read, update, and delete data in a database. Now, this is short for, sorry, this is long for the acronym CRUD. You're going to see it everywhere, oh, CRUD operations, and so on and so forth. You already get what these three words mean, but then for read just means that you're fetching or you're getting data. So we have some functions of a database management system here, but the definition says it all actually. So this will just be for extra reading and you can go through it. Okay, the one function here that is really important is data integrity. So let's understand data integrity. It says that it's the accuracy, consistency, completeness, and reliability of data throughout its entire life cycle, thus protecting it from corruption, from loss or unauthorized changes, making it a trustworthy asset for decision making and operations. So, what do we mean by accuracy normally? It means that the data that you have is free from errors and it reflects real world facts. So, let's go back here. Um, let's see that. Let me change this. Let me add something. So, program. So let's say we have a student of ID1 and the name is Jim and the email is jim@example.com and Jim's program is SEF, right? Another student, Loved, Loved@example.com. His program is also SEF. Now let's say that in the course of interacting with this data, some way, somehow, Lovet's information changes to SEP. Is this data accurate? Not anymore. Why? Because it has an error and it no longer reflects real world facts because there is no program that exists as SEP to begin with. Now, let's talk about completeness. It says that all the necessary fields are present. All the necessary fields are present. Just as the word complete is there, nothing should be missing. Take this for example. Alice, for example. Alice doesn't have a program. Alice doesn't have a program, that is incomplete. Or let's say there are supposed to be three students here, right? And then, sorry, and then all of a sudden, we no longer have Lovett's information. This data is no longer complete. What about consistency? Consistency means that the data appears the same across different systems at different times. So let's say that in our database, we have Lovett's information here, right? And then the moment we, let's say, export this data to use on some other tool or some other platform, um, Lovett's information has changed or Jim's information has changed. It's no longer consistent. Why? Because it does not appear the same on database one or platform two, and so on and so forth. Now, reliability. Data is stable and it produces consistent results. This reliability is more like a summary of the previous points. If your data is not accurate, if it is not complete, if it is not consistent, depending on what you're doing, then definitely your data cannot produce consistent results, cannot produce stable results. So some examples of database management systems we have include MySQL, Oracle, PostgreSQL, MongoDB, there's equally Cassandra, even some vector databases that exist. Vector databases, the data guys will be more concerned with this. There's also Microsoft SQL Server and so on. Remember, it is the software that you use to interact with a database. All right. So, so far, are there any questions? Love it. If you're speaking, I cannot hear you.
My lines are breaking. I spoke.
Okay, I was asking if there are any questions. What are you saying?
That so far I'm listening.
Okay, Jim, what about you? Jim, are you there? Alright. Alright, so let's continue.
Okay.
These advantages work for you to read on your own. So for types of databases, yesterday we talked about relational databases, non-relational databases, others, OOP, object-oriented databases, cloud databases, distributed databases. So relational databases are what we're going to be working with specifically in this program throughout this entire course. And the exact relational database management system we're going to be using is PostgreSQL. For non-relational databases, another name for a relation is a table, right? Meaning that it actually has structure. Although PostgreSQL implements some non-relational database features, which we are going to see. For example, we can store JSON data in a column. Okay, but that's some information for later. So non-relational databases, meaning that it stores data that is not structured. So it can either store semi-structured data or it can store data that is not structured at all. For object-oriented databases, I think I put an additional resource on this for you to read. But then it just takes that whole concept of OOP, data existing in the form of classes and objects. Okay, yes, there's a resource here on it. What else? Let me see. Mm, Okay, for distributed databases, I think you were there yesterday when I was explaining what this means. When we talk about distributing your databases, what does it mean? Robert, are you there?
Yes, I'm there.
I'm waiting for your response.
Distributed database. As dis- distributed databases, this system, as the name describe it to be, will simply mean the gathering of 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 databases, um, the gathering of databases across different sources.
Mm, when you say across different sources, like do you mean like it is spread across different sources?
This what did you say?
Do you mean that it is spread across different sources?
Yes.
All right, you're almost there. There was something which I explained yesterday. I'm going to put it again on Discord so that you guys can use it. You guys can take it as an assignment and learn more.
You put it in the classroom.
Yes, on Discord.
Okay.
Let me just put now. Um, all right, it's there. Please try to look at it. Okay. So let me see. Then for cloud databases, it just means that a database that exists on the cloud. What is a cloud?
The cloud.
Yes.
The cloud is a space where servers share resources.
Server share resources. What is a server?
A server is a supercomputer that solves, stores, and manages resources.
Stores and manages resources. So how exactly does it manage these resources? I want to be sure that we're on the same page. Just tell me what you know.
Okay. They manage resources by um, executing tasks and protecting information.
So how does it protect the information? Again, I just want to know what you know. I mean, we're here to learn, right?
Mm, okay, they, they protect information by one way by um, setting firewalls.
Okay. Setting firewalls. You know, you tell me what a firewall is. I want to know what you know, love it. Please, you don't have to Google things to answer these questions.
Okay. Uh, I think I wrote what the firewall was somewhere.
All right. I'm waiting to hear.
It's a firewall. It's a security system. It's a network security system that manages incoming and outgoing traffic.
Okay. All right. All right. All right. All right. Okay. That's okay. It's correct. So back to relational databases. Please, these additional resources that are at the bottom right,
Yes.
try to look at them. There's a lot of helpful information there. We can't say everything during our class. So please try to take a look at them. Okay. So let's look at relational databases in detail, since this is what we're going to be looking at throughout our entire program. So we already established that a relational database stores data in the form of tables, right? And another name for a table is a relation. So hence the name relational databases. All right, but then these tables consist of two key things, rows and columns. So the row is what is horizontal, the column is what is vertical. Rows can equally be referred to as tuples or records, and columns as attributes or fields. This is an example of a student table in a database. So you see we have the student ID, we have the name, and then we have the course that the student is taking. Right. So student ID, this is a column or a field. Name, this is another column or a field. Course, this is another one. But then you see where we have this 101, Alice, CS, and if there were more columns, definitely there'll be more entries, making the row longer, right? This is what we
Yes.
refer to as a row, these horizontal ones. All right, so some key concepts in relational databases. Just a minute again. Okay, sorry. So tables, we've already established what tables are, right?
Please, I did not get what you're saying.
I'm saying for tables, we've already established what they are.
Okay.
Yeah, and then every table, each table represents one entity. For example, you could have a student table, a course table. If you were to design a database for some real world scenario, or I don't know what to put it. Let's say if you were to design a database for an e-commerce platform, for example, what entities are you going to have? Or let's say, okay, if you were to design a database for a mall, or for a bakery like Jeffobi, for example, what entities are you going to have?
Customer.
Customers, that's great. What else?
You said them all, right?
Yes, a mall.
Stores.
Stores, yes, yes, yes. So you said customers, stores, what else?
If there are stores, then there will obviously be a store owners.
Store owners. Mm, mm-hmm. Yes.
Um,
I mean, Daniela, you're also here. This is good. Jim, Lovett is not the only one to participate, so you guys can answer the questions. So, Lovett, let's work with this so far. Customers, stores, store owners, right? Now,
yes.
in the customers table or entity, what fields, what columns can we have? What attributes? Where is it? What attributes? Remember what an attribute is. Normally, an attribute describes something, right? So, what items can you have that would describe a customer?
Uh, Customer ID,
ID, yes, what else?
name,
Name, anything else?
gender,
Gender, yes, even their address,
yeah,
and so
address, yeah,
their
email.
email, that's great. Even when they became a customer, right? So you can have something like created at when they became a customer. All right. Then for stores, what are some attributes that would have?
mm,
Of course, we'll have an ID. What else?
mm, Store name,
Yes, the store name. What else?
the address of the store in the mall,
Address of the store. Let's just say location,
yeah,
right?
location.
Like top floor, bottom floor, all of that, right? Um, what else? Don't you think it'll be interesting to know who owns the store?
Yes, store. Yes,
Store
store
owner,
owner. Yes.
right? Okay. So I'm going to come back to this store owner. All right, but then Under store owners, what should we have? We have the ID. What else should we have?
the name,
The name and
the
maybe email, gender, and
email,
so on.
yeah.
Yeah, all of that data. Okay, so now in the stores table, customers table, store owners table, and so on, you see we have the ID. And I said that this ID uniquely identifies each row in a table, right? So the column in a table that uniquely identifies each row in that table is referred to as a primary key. Does that make sense?
Yes.
All right. Now, let's say um, for a customer table, let's say we're supposed to have some entries. Let me change. My keyboard is speaking another language. 1 minute. All right. Let's say we're supposed to have some entries: gender, address, email. If we're to have these entries, what are we going to put under? So ID, let's say it is one, right? Name, let's say Miriam. Gender, female. Address, Oya. Email, Miriam at example.com. Created at, let's say 30/01/2026, and then we can say 2 p.m., right? If we're to have another entry for somebody, another customer, let's say love it. Let's just leave the rest of this information. No, let's
No,
leave the
I'm
rest.
not sure.
I've changed it. All right. So this can even happen in a table. Normally, this should not happen in a table. Why? Because this field should uniquely identify each row. So what happens is that your ID now would maybe be two or three or four or five or some other number, right?
Yes.
Okay, this is what a primary key does. Now, in the stores table, we also have the ID, which serves as a primary key, the name, the location, store owner, and so on. Okay, but now you see here in the store owners table, we have the ID primary key, the ID, which is a primary key, right? But then in the stores table, you said that we have to have a store owner so that we know who which of the store owners in the store owners table owns a particular store, right? So what we're actually going to have here is the ID, right, of that particular store owner referencing this store owners table that we have here. So okay, let's say for a particular store, let me visualize it. Let me put it like this so we can see. Mm, store owner ID. So let's say for a particular store of ID1, store name is, let's say, B complex, location, top floor. Who owns this store? Who owns this store? Are we going to start putting all of the person's information here again? No. So let's just say the person who owns this store has an ID of one, meaning that when we now come to the store owner's table, mm, email. So when we now come to the store owner's table, we are looking who is the person that owns this store. Jim at example.com. Who is the person who owns the store? Okay, we're like, okay, for this particular store, B complex, which is on the top floor, the store owner has ID1. But who is the store owner of ID1? Jim, right? If there was another store, maybe Y complex this time around, bottom floor, and the store owner ID is still one. Okay, well, like, so yes, Jim owns Y complex and he also owns B complex, right? So
Yes.
yeah, in this store table, this ID, this column that references a primary key in another table is referred to as a foreign key. All right. So we're going to see more on that as we move further. Let me see. Okay, yeah, we've talked about primary key and the foreign key. So this is actually good. I'll keep this. Maybe we may come back to this example. All right, but then among tables in a database, among the various entities in a database, we have what we call relationships. So what we've already seen here is an example of a relationship. You're seeing that okay, in the stores table, there's a store owner ID that links to the store owner's table. Hence, there's already a relationship here. So there are four relationships here. There are four relationships here. So the first one is the one-to-one relationship. Now, for the one-to-one relationship, just pay attention. For the one-to-one relationship, it is explained as this. Each row in a particular table, let's call that table A. Maybe I should zoom this out. Yeah. Can I increase? Nice. So each row in a particular table A has is related to at most one row in another table B and vice versa. One-to-one relationship. Each row in a particular table A is related to at most one row, at most meaning that that is the maximum, right? At most one row in another table B, hence a one-to-one relationship, and vice versa. So each row in B is related to at most one row in a particular table A. So there's an example we have here. Let's say we have two tables. We have the person we have the person table, and by the way, please, it is we're giving all of these table names here with in plural form: customers, stores, store owners. It is good practice for it to always be in singular. So instead of maybe saying store owners, it should be store owner. Instead of stores, it should be store, and instead of customers, it should be customer. So let's say we have a table here called person. So some attributes in the person table would include the ID, right? To uniquely identify that person. What else? We would also have, say, the name of the person. Now, what we want to do here is that we want to see how a person owns a passport. We want to establish that one-to-one relationship. So in the passport table, definitely we'll also have the ID to uniquely identify each passport, right? And then who owns the passport? We now have the person ID coming in, which is a foreign key, right? Referencing this ID column in the person table. Now, in the passport table, maybe you can have other information like maybe the center where it was created, when it was created, and so on and so forth. This is a one-to-one relationship. One person can own one and only one passport. In a similar manner, one and only one passport can belong to only one person. I know you may want to say that okay, in the real world, people own multiple passports, but normally, even with your ID card, the document is just meant for you and you alone, right? You should not be having more than one. So that is an example of a one-to-one relationship. Is it good so far?
Please, please, Miss Miriam, can you take it back from the foreign key concepts up on the store owner?
All right. So I was saying that yeah, in the mall, right? You said that these are the entities would have customers. Oh, not bad. Let me see. Oh, Notepad is getting better. I can even bold stuff. All right. So these are the entities, right?
Yes.
In the mall database. So we have customer stores and store owners. Okay, now, by the way, I said that I don't know if you heard that part. It's good practice for all of these entity names to always be in singular and not plural. So in the store table or in the stores table, the ID, which serves as the primary key, uniquely identifies each row, right?
Yes.
There. But then for a particular store, you want to know who owns that store. So maybe instead of coming to have something here, maybe to know who owns a store, instead of coming to have something like this, okay, um, store owner name, store owner address, store owner whatever, email, right? You see that it's just too much. Everything relating to one entity should be stored in a table specifically for that entity, right? We should not come and start having lots and lots of unnecessary information in an entity that is not even related to it. So all of this information now ideally should come and sit in the store owner's table, right?
Yes.
Okay. Now, for a particular store, we want to know who owns that store. So instead of coming to put all of this information, we just take the ID of that store owner from the store owner's table, right? From the store owner's entity and reference it inside the store's table. So because we've referenced it like this, if you want to know, let's say, who owns a particular store, B complex, this is their ID, right? We just come now to the store owner's table and like, okay, who is the person that has ID one? Jim. Okay, meaning that Jim is the owner of the B complex store.
How
You
how the how the how the database be able to uniquely identify that this ID belongs to store owner ID and not maybe customer ID if they have the same value. Like let's say like Jim's ID is one and then my
yeah,
customer ID should be one.
it's not an issue. It's a concept that we're going to look at when we start writing queries called joins. You're going to see how to join tables on different conditions such that you're able to pull out this information. But now I
Okay.
just need you to get the high level overview.
Okay.
All right, but that was a good question. Okay, so now this column in here, this store owner ID, this column here in the stores table, it is referred to as a foreign key. So a foreign key is a primary key of an entity, right, of or of a table that sits in another table for the purpose of referencing. So now we're here in stores. We want to know who owns the store. So instead of putting all that information, we just take the store owner's ID. So we're referencing this primary key here in another table, right? This other table still has its primary key, but because we are referencing this one in this other table, it now becomes a foreign key. You're a foreign item here. Okay, just get the whole idea. Is it clear so far, Lovin?
Yes. Thank you.
You're welcome. Daniela, are you with us? I know this is revision to Daniela. Okay, Lovin, it seems you're the only one in this class today. So I was explaining relationships, and I said there are four relationships, right? There's one to many, there's one to one, sorry, one to many, many to one, and then many to many. So this is what I was explaining here for many to one, for one to one, sorry. Let me write one to one. Yeah. So I was saying that for one to one relationships, right? Each row in a particular table A is related to at most one row in another table B and vice versa, meaning that each row in B is related to at most one row in another table A. So this was an example I was giving using person and passport. You have the person table, in this case it can be our table A, right? And then we have the passport table, in this case our table B. A and B just represent anything or any entity in this case. So in the person table, you have attributes, columns or fields like ID and name, right? ID here being the primary key. And in the passport table, you would have the same ID, perhaps the center where the passport was created, when the passport was created, hence created at maybe even the type of passport. Yeah, that there are different types of passports. One that can even permit you to travel to a certain number of countries and so on. Okay, but then how do we know who owns a particular passport? Instead of coming to copy all of the person's information like name, date of birth, address, gender, email, phone number, mother's name, father's name, that's a lot. What do? We introduce a foreign key in the passport table that references what? The ID, that references the person, right? Hence the ID in the person table. So one person, let's explain this one-to-one relationship because we said one row in table A should relate to at most one row in table B and vice versa. Okay, so now for the person table, one person should own at most one passport, right? And in a similar manner or conversely, one passport should belong to one and only one person. Do you understand the one-to-one relationship?
Yes.
All right. Let me see. Is this stream still going on? Okay. All right. That's great. So now we have also the one to many relationship. One to many. All right. We have also the one to many relationship. And in this relationship, one row in a particular table A can relate to many rows in another table B. But each row in that table B in turn relates to only one row in table A. Let me copy this and then give an example. So we can say 1 to n. It can be represented like this with this column symbol, or you can also write it like this, or m, whichever you're using. All depends on you. Okay, so let me give you an example. But notice that the many table, which in this case is B, right? Remember, one row relates to multiple rows in the other table. One row in A relates to multiple tables in B, but multiple tables in B relate to one row in A. So the many table, which is B in this case, contains a foreign key that references the one table. Let's take an example. Let's have a customer table, right? Okay, so let's go back to what we had up here for your malls table, for your malls database. So we have the customers entity, store entity. Let me remove all of these S's so we will say it. Okay, now in that mall, of course, customers must buy because what are they doing there? So we can have a purchase table, right? A purchase entity that relates to that gives us information about the purchases that have been made by customers or by a customer. So what are we going to have? We're going to have the ID table to uniquely identify the ID row, sorry, column, the ID column to uniquely identify each row in the purchase table, right? But then we may want to know, let's have other information like, okay, when that item was purchased, purchased at. We may also want to know from which store it was purchased, right?
Yes.
So this becomes a foreign key. Of course, we may also want to know the exact item that was purchased. This can be another foreign key, or it could still maybe just be the item name. Now, we could also, let me see, have other information like what can we say? Maybe payment method. What was used to pay for the item that was purchased, right? Maybe it
Mm.
was Momo, cash, and so on. All right, but then one thing that is also interesting here is who made the purchase. Who made the purchase? So definitely we're going to need the customer ID, which would be another foreign key. Now we're talking about the one-to-many relationship. So one customer, right, can
Yes.
make one or many purchases, right?
Yes.
But then several purchases can belong to a single customer. True or false?
True.
Now is the one-to-many relationship clear? Or do you still need some explanation there?
No, no.
Okay, all right. So there's now the many-to-one relationship. So the many-to-one relationship is the same as the one-to-many relationship, just from another direction. So you're basically, let me write it so we can see. Mm, all right, for the many-to-one relationship, we're basically saying that many rows in a particular table A can relate to one row in another table B, and one row in a table B can relate to many rows in a table A. So it's just the opposite, but the same thing. Okay, now we have another one, which is the many to many relationship. What do you think it is? Try to explain it to me, given what you've gotten so far on one to one and one to many.
So many rows in a table can relate to another table's rows.
Yes. So many rows in a table A or rows in a table A can relate to many rows in a table B,
B.
right? And
Yes.
vice versa. And vice versa. Now, how do we implement this many to many relationship, let's say in our database? How are we going to do it? We do it using something that we call a junction or a bridge table. Junction or bridge table. This is how we implement many to many relationships. And usually, these many to many relationships, they often use what we call a composite key, or it can still be referred to as a composite primary key. Let me put this in bracket. Primary. Yeah. So let me give you an example. Let's try to visualize it so that you're able to understand. Okay. So let's say that we have a school database, right?
Yes.
Um, school database. And in that school database, some entities that we would have would be students, right? What else? Course, and then enrollment, student course, and then enrollment. What are some attributes that will exist under the student entity? Would have the ID. What else are we going to have? The name, say the matricle number, right? What else are we going to
Yes.
have?
Because
Email. Come again.
but the student must be taking a course now.
Yes, the student must be taking a course. So let me put this here and I'll come back to it, what you said about the course. So if the student is taking a course, then definitely instead of coming to put all the course information, we should just put the course ID, right?
Yes.
yes, to reference it. And this will be a foreign key. Nice. So in the course table, of course, we'll also have the ID, course name, um, maybe course timetable, something like that,
Mhm.
and so on. Okay. Now, let's try to visualize this. Let's have some entries for the course table. So ID, course name, timetable. Okay. So ID, let's say one. Course name, geology. Geology. Am I spelling it right? Geology. So timetable, let's just say Monday, right? Next
Yes.
course, physics, Tuesday. Next course, what can we have? Math, right?
Yes.
And math, let's say math also holds on Monday. Now let's try to look at the student table. So we have ID, we have name, um, we have matricle. I'm going to leave out this email. It's just too long to write. Let me just put them already there. And then we also have the course ID. So student ID is one, right?
Yeah.
Name, Loved. Loved's matricle is 12345, for example. And his email is loved@test.com. Loved is taking geology, right? So put him
Yes.
ID1.
Yes.
Okay. Another student, let's say Daniela, her own matricle is 12346. Email danny@test.com. Daniela is taking, let's say she's also taking geology, right?
Yes.
But then again, Daniela, of course, her ID must be the same since it's the student table, right? Daniela is also taking, let me see, 1, 2, 3, 4, 6. Danny test, should have just copied this. Daniela is also taking physics. Daniela, as a matter of fact, is taking multiple subjects. So she's also taking math, for example. Let's say there was a fourth subject, English. Daniela is equally taking English. Now, if Lovell were to do the same, if Lovell were even to take two more courses, let's put, um, so let's say you're taking course 2 and course 4. This was supposed to be 4. Do you see what's happening? This primary key column that is supposed to uniquely identify each row is no longer unique. 2, 2, another 2, another 2, and so on. There's one here, there's one here, there's one up again here. It's no longer unique. It's defeating the whole purpose of this primary key column. Okay. Now you realize that in trying to do this, right? In trying to do
Yes.
this, we're implementing what is referred to as data redundancy. I think you see the term there in the notes. I'm just going to put it down here.
Yes. You
So,
spoke. You spoke about yesterday.
okay. So what is data redundancy?
So when data is monotonous.
Wow, that's a big word. I don't even know the meaning. So,
It's repetitive. As
okay, it's repetitive. Exactly, it's repetitive. So
wait, is sorry, is redundancy different from redundancy?
another big word. I don't know. Let's Google what redundancy means. Redundancy. Let me see. Is redundancy even a word? redundancy meaning. I'm not seeing redundancy as a word, but you can
Okay.
look it up. Perhaps I'm just doing a quick search and not paying attention. You can look it up and then you tell me.
Okay.
Okay, but then back to the point. There's a lot of data redundancy here, repetition of data, right? Which
Yes.
does not make sense. Why are we doing this? It's just too much. And this is also bad design. When we get into database design, you're going to understand this further and then even talk about concepts like database normalization. But for now, remember we're talking about the many to many relationship. And we said that to implement this many to many relationship, we introduce a junction or a bridge table, right? And usually it will use what we call composite keys or composite primary keys. So let's see how this will go. Let's normalize this database. You get more familiar with the word. So in the enrollment table, we know that one student can be enrolled to one course, right?
Yes.
One student can equally be enrolled to many courses. Now, many students can also be enrolled to one specific course, and many students can be enrolled to many courses. Taking it from the other side, okay, many courses are being taken by many students, many courses are being taken by one student, and so on. So this enrollment table here now is going to serve as a junction or a bridge table for implementing this many-to-many relationship. Let's look at some of the attributes we're going to have here. So we'll have its own ID column, which is going to serve as a primary key, right? And then we will now have the course ID, which is a foreign key, and then the student ID, which is another foreign key. Before other information like, okay, enrollment time or enrolled at, get the time when the students enrolled, right?
Yes.
Okay, maybe some other interesting information. Now let's try to visualize this and make this student database less congested by taking out this course ID field. So let's look at this. We'll have the ID, we'll have the course ID, we'll have the student ID, and then we'll also have enrolled at, representing the time when that particular student enrolled in a particular course. So let's say ID 1, right? And
Yes.
then for the course geology, for the course geology, or let's take it from here, yes, for the course geology, the student Lovett enroll. Don't mind all these ones I are saying, it just represents the ID. The student Lovett enroll, let's say, don't want to rewrite this. I know I wrote the date here somewhere. Okay. Enroll today, 30th January at exactly 2 p.m. Right? Now, for the other course, let's see what other enrollments we had here. Okay, for the student now, Daniela, she also enrolled for the same course, right? So
Yes.
we're going to have course ID 1, um, student ID 2. She enrolled at the same time. What other enrollment do we have? Daniela still, but she enrolled for the physics course of ID2. So I'll just copy this again. This now would be 3. She enrolled for physics. I think Daniela even enrolled for multiple courses, right? She
Yes.
enrolled for all the courses actually. So let me put this here for course ID 3 and then student ID 2. Now let's give Lovett another course. This would be 5. Let's say Lovett enrolled for the course 2 and his ID is 1. Now, you see that now we have the enrollment table. It serves as a junction, a bridge, right, between
Yes.
the course table and the student table. Now, this part of using the junction or bridge table to implement this many-to-many relationship is actually clear. But then, what about this part? We said that the composite, we said that it can also be uniquely identified using what we call a composite key or a composite primary key. So, a composite primary key is basically two primary keys that are sitting in another table as foreign keys.
Two or more, or just two?
Two or more. It's possible to actually have more.
Okay.
All right. So yeah, let's take a look at this. We have course ID one, who is taking it, Lovett. This pair is unique, right? We
Yes.
have another course one, but who is taking it, Daniela. We have another course still being taken by Lovett. It's still unique. No matter what, Lovett, who has already enrolled for, I think this was physics, can never
Yes.
enroll for physics again. Why? Because it's already enrolled. In a similar manner, you can't enroll for geology again because you're already enrolled. Same goes for Daniela. You see, every pair here is unique, right? Hence, we
Yes.
call it a composite key or a composite primary key, meaning that this ID column, which we have here, is practically useless. Do you see?
Mhm.
Because this pair already uniquely identifies this row. This pair already uniquely identifies this row. So we no longer need this anymore. Is it clear?
Yes.
Okay. All right. So this is it on relationships. That's actually an overview. Okay. Now we've been looking at all of these things, but then we've been looking at all of these things, sorry, at a high level. Before we even go into this next part of the lesson, SQL, that's structured query language, the language that you use to interact with these databases, these relational databases. I want us to look at some data types. Now, when I talk about data types, I don't mean the categorization of data or by nature, by structure, and all of that. No. So, some data types that commonly exist are, let me put up here. We have what we call string, we have character, we have number, we have boolean, we have date, date time, and so on, right? So, a
Yes.
string is basically a sequence of characters, usually put in quotes, single or double quotes, right? And an
Yes.
example of a string is a name like Loved, for example. Now, a string does not necessarily mean that it must be letters. Remember, it's a sequence of characters. Sequence of characters. Meaning that we could still have numbers in here. A string could still be a matrical number, say SCF 21001, for example.
Oh, oh,
This is still
like a
like a
license plate.
like a license plate, exactly. Like a license plate. How do they even write those things? SW.
Let's just assume this. Okay.
Yeah, let's just put this. Let's just say this is the license plate number, right? So this is a string, a sequence of characters. Now, what is a character? This is an example of a character. When in quotes, this is another example of a character. Just a single item in that string, just a single item in that string is referred to as a character. Now, what about numbers? Numbers, you can have integers, you can have floats, you can also have what we call complex for complex numbers that have complex numbers and numbers that have real and imaginary parts. Right? But you see most of this. So an integer, like how we're talking about discrete and continuous data, right? An integer is a positive or negative whole number. An example of an integer is 11, -5, or -15, and so on. But then a float, we can have 2.56788, this, that. That's a float. It could still be negative. It could still be negative. So we could have something like -1.00004, for example. That's a float. But then a complex, a complex number has a real and an imaginary part. So you can have something like 0 plus 2j, 0I plus 2j. Now, for a boolean is anything. It's a data type that represents data that only has two states: true or false, one or zero, on or off, up or down. Two states. So you usually see true for boolean like that, and then false when something is not true, of course. Then for date, this is an example of a date, right?
Yes.
This is an example of a date. For date time, it means that it is date and then time. Then for time, it is just the time. There's even date time with time zone, where you now start having this date part, the time part, and then information on the time zone. Maybe something like +1 to represent T or UTC +1, +0 to represent GMT +0, -3 to represent UTC plus -3, and so on. Right? So there are many data types that exist around date and daytime thing. Okay, so this date, just to give you some context, it is using this format of what is the date slash month slash year. It's using that format. In a similar manner, the time is using this format of hour, minute, second. This is just an overview on data types. So
Yes.
in your customer table, for example, you have ID and you're seeing the values here, 1, 5. What kind of data type is this?
It's a character.
No, no, no. It's an integer for number, right? It's an
Yes.
integer, positive or negative whole number. Are you seeing?
Yes.
What about name?
It's a string.
Good. Name is a string. In databases for strings, especially PostgreSQL, you usually see something like text or varchar. This still represents strings, just another way of saying that, okay, this is a string, but then I'm specifying that it is this kind of string or it is that kind of string. So in simple terms, very large string, string that is not very large. So yeah, you're correct. It is a string. What about gender?
It's a character.
Yeah, it's a character. Good. An address?
So address.
Yes, address.
Address is also a string.
Good. Address is a string. What about email?
Email is a string.
String. And then this created at when they became a customer. What is it?
Date time.
Good. Date time. So let's say we were to have another field here, like let me say has completed KYC. What do you think the data type should be? It's either the customer has completed KYC or hasn't completed KYC. So what do you think the data type should be?
Boolean.
Exactly, Boolean. That's good. Okay. So back to this SQL. Structured query language is a language that is used to interact with relational databases, right? And these are some common SQL commands that you're going to see us using: select, insert, update, delete, right? This gets
Mm.
data, this adds data, this modifies data, and this deletes or removes data. So, advantages of relational databases and limitations. This is for you to read and do more research on. And we already said that some examples of relational database management systems are MySQL, PostgreSQL, Oracle DB, Microsoft SQL Server. So for this course, we're going to be using PostgreSQL. For non-relational databases, okay, I think we already talked about this and gave examples like MongoDB. They store data that is either unstructured or semi-structured, right? And
Yeah.
under it, um, we had some examples, okay, key value databases, document databases, column-oriented databases, graph databases, and so on. This is just like really nice to have knowledge, so please do well to go through it. Okay, then there are other types of databases: object-oriented databases, distributed databases, cloud databases. We talked about this already. In-memory databases, this is what is just stored in your disk on your local computer, and it's very fast because I mean, if you're accessing it from your computer and it's stored on your computer, then speed is like instant. And an example of this, by the way, is Redis, and you're going to see how to use Redis in more detail when you get to a later part of the cohort. So Redis is used for something called caching, like just storing information that you can easily access later on. More details on that later.
Mm.
Okay, here we just have a comparison with relational and non-relational databases. So it's basically just like a summary table for all that has been discussed above. So for these additional resources, you should please go through them, understand this data integrity, the data lifecycle. I even drop something here on database design just so you have an overview, although we're still going to get into it in detail. But then something that I want us to look at before we even move to the next lesson is on these transactions. So we have OLAP and OLTP transactions. What do you think is a transaction in a database?
A transaction is the exchange of uh, data between two tables.
Mm. Well, I understand why you're saying that, but that is not exactly what it is. So it's just a unit of work, right, that is done in a database. And this unit of work is done using CRUD operations. So if you add data to a database you've created, right, you've used the create operation inside CRUD, and as a result, you've carried out a transaction. If you're fetching data, that is a read operation. That's a unit of work. So as a result, you've carried out a transaction. The same applies for when you're updating and when you're deleting data. So let's just say it's an action that you perform in a database. So before even going into this OLAP and OLTP transactions in databases, let's look at what we call ACID properties. ACID properties. All of these ACID properties are related to transactions in a database. So ACID, where is ACID like this? It's an acronym where we talk about A first, atomicity. C is for consistency. I is for isolation, and D is for durability. So let's look at this in line with database transactions before even going into the OLAP and OLTP in databases. So when we talk about atomicity, atomicity is basically saying that every single transaction in a database is treated as a single individual unit that either fully completes or fully fails. And the goal of this is to prevent partial updates. So you know what an atom is? I think in physics or chemistry, they'll tell you that it's the smallest unit particle, that kind of thing. The same applies in a database. It's a single unit, single indivisible unit of work that is done, a single indivisible unit of work that is done, a transaction, right? That either fully completes or fully fails so that we avoid partial updates. Let's take an example of a Momo transaction. I think we're going to use this example all through to define all of this. So let's take an example of a Momo transaction. Momo transaction. So if a Momo transaction is supposed to happen, it happens between two people, right? The sender and the receiver. So let's say that the sender has a balance of 10,000 in his phone, while the receiver has a balance of 0 francs. Now, before money is even sent, the sender, of course, must actually have this balance. Now, let's say that this sender wants to transfer the amount of 1,000 francs from their account to the receiver's account. What does this mean? That their balance should now be 9,000 francs, and then the receiver's account is credited, changing their balance to 1,000 francs. What happens here is that if this is actually the true state of their account after he initiated the transaction, okay, his balance becomes 9,000, the other person's balance becomes 1,000, then it means that this has fully completed. Now, let's say in the course of sending, right, there was some issue and this money could not go entirely. So their balance still remains the same. What does this mean? It fully failed. But imagine that in the course of sending, there was some issue, right? Some network issue or MTN config issue, whatever it is. And the money actually reaches the receiver. But then the sender is not debited. This becomes an issue. There's a partial update. Are you there, Lovin?
Yes, I'm there.
All right. So this becomes, just give me a minute. Okay, so this becomes oh, that's saying okay. So this becomes a partial update, right? Or let's take the case where this person actually sends the money, but then for whatever reason it never reaches the person's account. It's an issue. So it is also a partial update. What does this mean? This transaction that is here does not now sit in line with these acid properties, atomicity to be specific. It did not fully complete, neither did it fully fail, hence there's a partial update. There's an issue. All right. By the way, all of this is linked with data integrity, right? Because if you, let's say you were to have a transaction stable or the user stable with their balances and everything, and the balances do not reflect the true amount at a given point in time, then what does it mean? It's not accurate. So all of this is linked to data integrity. Remember, is the accuracy, consistency, what's the other one? Completeness and reliability of data. Okay, moving forward, let's talk about consistency. So this is done. We've ticked it. Let's look at consistency. So with consistency, it ensures that transactions move the
Mm.
database. Are you there?
Yes, I'm there.
Okay. It ensures that transactions move the database from one valid state to another, following some predefined rules, preventing, sorry, um, preventing something that we call race condition. Let me see, what example can I give you? Okay. So let's take this. All right. So let's say we have, let me try to visualize it here. Let's say this is a transaction table, and then we can have maybe sender ID, receiver ID. Um, okay, this is really bad design, but then let's do it for the purpose of demonstration. Sender balance, receiver balance. This is our table. ID one. Let's say sender ID is LV1, for example. By the way, IDs must not always be integers. It could still be some strings that we make use of. In our case, we can make use of what we call UUIDs. More on that later, but I'll just put it here. UUID. Okay. Then we can have the receiver ID. Let's say JM1, balance 10K, receiver's balance 0K. So this is the initial state of the database, right?
Yes.
Okay, of let's say MTN's Momo transactions database. Now, with consistency, it should move the database from one valid state to another, following some predefined rules. So a predefined rule could be something like, okay, if a transaction fully completes, then the states, the amounts or the balances should change. So if the transaction fully complete, we're expecting to now see something like this. This should change now to 9K and then this to 1K. The goal here is to ensure the completeness of data completion. All right, this is one valid state of the database. This is another valid state of the database. So this is fine. But let's say that this fully completed, and then we still have this state after this successfully completed, then there's an issue. It's not consistent. Is it clear?
Yes.
All right. Then with isolation, isolation makes concurrent transactions appear as though they happen sequentially, preventing interference between them. And this is solving the problem of race condition. Like I said, race condition for consistency. Consistency is for data completion or completeness of data. Let me put here data completion. And here we have race condition. So before we even get into this isolation again, let's try to look at race condition. So let's say that um, we have three chefs in a kitchen. Three chefs in a kitchen. Chef A, Chef B, Chef C. And they are all preparing a meal. So Chef B is maybe frying an egg. Chef B is frying an egg and he's using the frying pan to fry the egg, right? Now, in order for Chef B's egg to be complete, he needs salt. But then Chef A is boiling rice. He's using a pot and he's also using the salt, which Chef B is waiting for. Now, Chef C, in his own case, maybe he's boiling plantains and mm, okay, no, this guy Chef A is boiling rice. He's using the salt, right?
Mhm.
And he needs a pot. I'm really just trying to give a real world example here without saying processes and resources. But then, like, okay, this is a process actually, boiling rice, and then this is a resource that he's using, and this is a resource that he needs. Same thing here. This is a process for Chef B frying an egg. This is a resource that he's using, the frying pan, and then this is another resource that he needs, the salt. Okay. Now for Chef C, let me see. So Chef C is boiling plantains. He's using the pot that Chef A needs. And let's say what does he need? Let's see what he needs. He also needs, maybe he needs salt or something. I don't know at this point. He needs salt. So you see that um each of them are holding resources that they all need through their
Yes.
ongoing processes, right?
Mhm.
So this whole scenario here, what is it called? What is it called in computer science? Do you have an idea? There's a process that is holding a particular resource, we're waiting for another resource to complete, but there's another process that is also running, right? Because processes have different states, like it could either be starting, it has stopped, it's waiting, it's running. And
Mm,
yeah, and a process
it's
just got,
is it deadlock?
yes. Exactly, it's deadlock.
Yeah.
um just give me a moment. Mm. Okay, yeah, so this is the process. This is referred to as deadlock. You mentioned you did computer science, right?
Yes.
Okay, means this is just revision to you. Okay, now let's look at race condition. Let's look at race condition specifically. So race condition, you have multiple processes, P1, P2, up to Pn, that are running simultaneously and are also trying to access shared data at the same time. So all of these processes up to Pn, they're all running. This is their state. But then they all need a particular resource or some particular data at the same time. Let's call this data that they need dx, for example. This now introduces race condition. I think from the name even, it's just it's just there. The definition is just clear. All right, so let's go back to isolation. With isolation, I said that it makes concurrent transactions appear as though they were happening simultaneously, preventing race condition, right? So what is a concurrent transaction? These are just transactions that are happening at the same time, simultaneously, in parallel, or however we want to put it. But then we need to implement, or isolation is important because imagine that every single user, or maybe every single request to the database is supposed to happen at exactly the same time. It's supposed to happen at exactly 7:36 p.m. At the first what was it at the first, it was it minute, it was this thing again, HHMM. Okay, at the first second, first millisecond or nanosecond, like exactly the same time. there's going to be an issue. It's going to introduce race condition, right? Because
Yeah.
multiple requests or processes or users or whatever are trying to access the same resource at the same time. Okay, now with isolation, all of these transactions that are happening simultaneously, that are happening concurrently, isolation makes it look as though they were happening sequentially. So if they were happening sequentially, what's going to happen? Okay, P1 will run first, maybe use this DX that they're all fighting for. P2 will also run after the P1, now using the DX that it also needs, right up to PN. Rather than that, all of them are trying to access it at once. There's going to be an issue somewhere if that were to happen. Okay, now let's look at durability. So durability, back to this Momo example, it guarantees that a transaction, that once a transaction is committed, that's committed means fully completed, committed, or if it fully fails, then it should roll back. Okay, so it guarantees that once a transaction is committed, its changes are permanent and will survive system failures, meaning that the data should not get lost. Even if the system happens to crash or get corrupt or as an intruder or whatever happens to it, this data should be durable. It should last. It should not get lost. This is what durability refers to inside its asset properties for database transactions. All right. So this, I think there's a resource on this too, so that you can further read. Now let's go to this OLAP and OLTP transactions in databases. So for OLAP stands for Online Analytical Processing, but I think we should even talk about OLTP first. So OLTP stands for Online Transaction Processing. This OL means online. And with OLTP, it's for handling day-to-day transactions in a database. So take for example, in a bank, right, or in some fintech or whatever. Look at this Momo example which I gave. Many people Many people are carrying out Momo transactions or bank transactions on a daily, right? And you need for that data to quickly enter somewhere and get saved. So for OLTP transactions, we make use of databases. But then for OLTP, by the way, deals with present data. Remember, it's dealing with current transactions. But then for OLAP stands for Online Analytical Processing. It deals with historical data. Now, the data that is used for this online analytical processing is stored in something that we call a data warehouse. What do you think a data warehouse is?
A data warehouse, it's a space that keeps data.
So, what's the difference with a database? A database is also a space that keeps data, isn't it?
But a database also represents the relationship, but I don't think a warehouse represents the relationship.
Really? Oh, no, that's not the case. Well, a data warehouse is basically still a database. But then its primary purpose is not to be storing current data, it's actually for historical data so that analysts, depending on the company or company size also, analysts can make use of it. Well, what are they called? Data scientists can also make use of it. Analytics engineers and all the like business analysts can also make use of it. So it's just there for doing the analytics, answering the questions, doing all the forecasting and so on. Okay, now with a data warehouse, let's actually see what happens before it has historical data and why a database has current data. I'm going to put this here. By the way, I can share this with you, this sheet. This notepad that I'm using, if you want,
You you say as a PDF or share link or what?
mm, the thing just exists locally. I'll just give you, it's a .txt file.
Okay.
I'll just put it on the channel. Okay, so for a database, let's look at it like this. You're at a bank, you're doing a Momo transaction, and today, hmm, how do I even represent this one? Today, let's call it day one or day zero. You do a transaction TX1, for example, maybe it was 5,000 um, deposit, right?
Yeah.
Deposit. I'm just going to copy this and use. On that same day, you still do another transaction of 5,000 and it's still a deposit. That same day, you still decide to do another transaction, let's say of 3,000, but then it's a cash out, right? So this will be TX2, TX3. And let's say that there are multiple people, end users, doing all of these same things simultaneously with you, cashing out, cashing in, and so on. So instantly, since these are day-to-day transactions, what happens? All of this data gets updated in the database in real time, right? So the database always holds current data. But then for a data warehouse, I'll say DB here, and I'll say DW here. All right. But then for a data warehouse, remember it stores historical data and it is used for analytics. So, unlike a database, a data warehouse does not always have the current state of is it information or transactions at a given point in time. Why? Because for data warehouse, typically they make use of what we call pipelines. Pipelines. Okay. Let's say you have a water source, for example. uh, let's say it's from a spring, right? From a spring. And what is flowing from that spring, what is coming out of that spring at that point in time is the current data. But then you cannot drink from that spring for many reasons. It's unhealthy, it is, in fact, primarily because it is unhealthy. So what happens? A plumber will have to come and connect the pipe, right? Say from the string to your house. And inside that pipe, there are different filters. Okay, maybe the first filter is removing rocks. Second filter is removing very little, bite size, little debris. And then maybe the filter now, when it gets to your house at the level of your tap, it's removing maybe any other dirt that was not caught and even passing chlorine through it to further sanitize it. And some people will even carry and boil and put inside a water filter again before they drink. But then get the whole concept. At the point where the water is reaching your tap in your kitchen, is that the current water? That water has passed through different, in fact, different stages before it is getting to you. So the concept applies, the concept is the same with the data warehouse. And a common pipeline that is used for this is what we refer to as ETL pipelines, or there are also ELT pipelines. And this refers to, in fact, the E is for extract, the T is for transform, and the L is for load. So however you put it, if it's ETL, it's extract, transform, load. If it's ELT, it's extract, load, transform. So what happens? Your data leaves the source, right, which is a spring, which is a database. And then in the course of it leaving the database, there are some transformations that are going to happen. Maybe removing columns that maybe are not going to be needed for the analysis, right? Empty rows that are there, either removing them or filling them with some information. If there are duplicates, for some reason, removing all of the duplicate data, some transformations are going to be done. These transformations, let's go back to the analogy of your water pipe. Those are the different filters that you have there that remove the rocks the other one removing all of those small particles and so on, before it now gets loaded into the data warehouse, which is the destination. Destination. Okay. Before it now gets loaded into the data warehouse, which is a destination. Okay, so at this point in time, let's say this is a pipeline, and of course this pipeline would have to run maybe at 12 midnight every day, or on Monday every week, or once a month, or whatever, all depending on the use or the company. Now, if something is run once every day, or once every week, or once every month, would it always have the current data?
If it's run once a month,
Yes, once a month. If it's run once a month, meaning that okay, on this particular day in a month, I should get the data, get all the data I need from the database, transform it, and then send it to the data warehouse. Will the data warehouse always have the current data?
yes,
The answer is no, Lovett.
no, that
But understand why it's no. Because
okay,
let's say today is the 30th and the pipeline has run. So all the data from the database is now sitting in the data warehouse, right? But
yes.
then tomorrow transactions will happen. Sunday transactions will happen. Monday, Tuesday, Wednesday, and so on until the 30th. Okay, February does not have 30th. Let's say until the 28th of February again before it runs. So before the 28th, is the data warehouse going to have the current data that sits in the database for all the transactions that have happened?
Mm, no.
No, exactly. But then analysts and scientists and so on can use all of that historical data now maybe to answer questions about maybe a user spending habit, to predict maybe how much income is going to be generated for the company, or how much someone is going to spend, and so on and so forth. I can't find the tab. Or is the tab? Okay. So, Lovett, this resource is there. We cannot go so much into it, but then you can read it. So
You
this
can't know.
you'll be here tomorrow,
No, I mean tomorrow there's an evaluation now.
but you've already read these things now. We're just doing revision.
Because it's not, it's an extra resource. So if it comes tomorrow, okay.
No, I mean definitely a question can come from these additional resources. They are there for you
Oh,
guys to read.
oh really?
Yes. Why do you think we put the additional resources?
For additional learning.
Additional learning. So we'll test the additional learning during the evaluation.
Okay.
All right. So this is it. This is it on introduction to, yeah, introduction to databases, or an overview of relational databases. So let me see. The next thing we're supposed to do is to actually set up PostgreSQL and get an overview of it and start running some queries. But
The
then
the link the link from of the setup here is it was not going on. I
which
had
one
to
we're using for which OS?
for yes the first link for Windows.
For
Very
Windows.
close. Yeah, it was disturbing. Deleted the setup
Come
back.
again.
I said I already deleted the setup to like do it again when you be teaching it.
Okay, that's fine. So share your screen, download, let's look at it, let's set it up.
Okay.
Although today I was also supposed to guide you guys on installing Ubuntu, but the others are not here and I'll not want to repeat it or have Yannick repeat it again.
Yes. I told Mr. Yannick that I will have to delay a little bit because the laptop that I wanted to use to download the Ubuntu is not this one. My junior is also using this one, and I don't want to change the software into something that she's not familiar with.
Okay, 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 okay. So
Yeah.
when are you going to get another one?
Well, I told him that tomorrow I'll take the laptop to the repair. So in the evening, I'll I'll endeavor that they should arrange it. So
All right.
yes, because we're supposed to. Normally, I knew that we're supposed to have a class with him yesterday. Then you were available instead of him. I'm sure it was because I don't know. I just assumed that was because I did not have the the
No, that's not
software.
why. We had to treat relational databases, at least look at it at a high level, because you're going
Yeah.
to meet tomorrow, and it shouldn't be that we didn't have it with the online guys. We had to
Okay.
start this, I think, last week, if I'm not mistaken. But then on the Friday that we were supposed to have a class, you guys were not available.
On Friday.
Yes, last week Friday we were supposed to have a class. So I just told him that this time around I'll take Thursday and he'll take Friday. But we had some electricity issues here, so the class got cut
Okay.
halfway.
Can you see my screen?
Not yet. Let me stop sharing.
Are you seeing it now?
No, not yet.
Let me see. How about now?
Yes, I can see it now.
Okay. I've already clicked the link, so it brought me here.
Okay. So under this Windows x86 64, download, yes, there. Download, click on it.
Okay. So we.
Yes. Oh, 5 minutes left. Means your internet speed is good.
Mhm.
Just call my attention when the download is done.
Okay.
Love it. Is it done? Oh, still like. All right. Let's just wait.
It's finished.
Alright. So click on the yeah. Just click on the file.
Okay.
Yes. Double. Just press enter or double click whichever. Okay. Take next.
Next again.
No. Untick that stack builder. You don't need it.
I want to untick.
Really. Click on it again.
Where? Hey, yo.
Why won't it untick? That's strange. Just as it's going to take a lot of time installing. Are you clicking like on the check? Yes, click there. Left click.
I even clicked even on my hand, my finger.
Oh, it's not bad to have it, but it's not just necessary. Anyway, take next. Let's see. So it says an existing PostgreSQL installation was found. The installation will be upgraded. In order to upgrade, we need to restart the server of the user. So, yeah, take next. Mm-hmm,
Based
mm-hmm.
on
It will be used. Yes, next. Next again.
next.
Yes. Please ensure PGRN is shut down. Do you have PGRN open?
No.
Okay, take okay.
Okay, so this is going to take some time.
Yeah, and some internet.
Oh.
Okay. All right. So I'm still here, but I'll just move my mic. So just let me know when this is done.
Okay. Okay. Huh? I should not do it for you. Which one?
So, Lovell, that's the file where we were practicing and giving all those examples.
Okay. It seems like I'll be the only one to didn't understand what is written there.
And Mike was muted. I was saying if the others don't understand, they would ask you, or as they're following along with the video, it will make more sense.
Okay.
How far with the installation? How many percent is it?
It's still loading. Can you see still my screen?
Yes, I can see your screen. All right. Just a little more time.
It's done.
All right. Stack Builder may be used to download and install. Blah, 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 blah. Can you try to, let me see, untick that box that has Stack Builder? Let's,
Okay, I've unticked it.
all right, just take finish.
Okay.
Is that all? Nothing else popped up?
No, let me try to go to the.
Okay. It's okay. It's okay. You got your Java soft skills certificate already?
Yes, I posted it.
Okay. All right. We'll check. Okay, so go back to the notes and look at the instructions which are there. So after you've installed, you have to add this the bin directory to path. So go open, just type environment variables in the search.
Wait, let me. You said, where should I go to, please?
Okay, you don't understand. Go back to your notes.
The notes here. My notes here.
Yes, your note here.
Okay.
You can just click continue on this relational databases. The
Okay.
one below, yes. Okay, so scroll down
Mm-hmm.
just a little, go back up. You've gone too far. Okay, so the first thing is that after installing, you must add the bin directory to your path environment variable. So you need to first of all find the bin directory of the PostgreSQL installation. So typically it will be in your C drive. So go to your file manager,
Okay.
click on this PC, this PC at the bottom on the left, yes. Then enter your C drive, go to users. Is it users or program files? Go to program files, sorry. Yes. Now scroll down, you should see Postgres. Okay, that's it there. Open.
Okay.
18, open. Bin, open. Okay, so at the top, you're using Windows 11. Nice. So at the top, you see where you have that drop down and that refresh icon, right?
At the
At
top
the
where I
top,
have,
where your path shows, where you see this PC,
yeah.
local PC. Yes,
Mm-hmm.
double click.
Double click yeah,
Yes,
or
double
just
click.
on this
Yeah, on the
empty.
empty space tool, go double click.
Mm.
Then copy everything. Control A is the shortcut.
Okay.
Okay.
Mm-hmm.
Now, in your search bar at the bottom on your taskbar, just search for environment variables.
Yeah.
Yes, there. Yes, click that edit and environment variables for your account. Okay, so you see where you have system, right? Or it could still be for your account, either works. But for system, under system variables,
Mm-hmm.
you have path. The text path. Path is under OS on your left. Yes, path. Click on path.
Mm-hmm.
Then take edit. It seems you can only edit for the.
Yes, I can manage it.
It's okay. Just go do it for your user. Same thing, path. Then take edit.
Mm-hmm.
All right. So click new
Mm-hmm.
and then just paste what you copy.
Okay.
Yes. Then take OK.
I've done it.
Done. Okay. Press OK here again.
Okay.
Yes. OK. Can you click this hide option? Besides stop sharing my screen. Stop sharing. Then hide.
Okay.
Okay. Nice. So open your command line. Just go back to search and type CMD. Okay, you already have it open.
Mm-hmm.
But I want a new instance. Click on the drop down.
Let me.
Yes, that drop down. Let me see what you have. Okay, you don't have Git bash. It's okay. Just open command prompt again.
Mm-hmm.
All right. So write this command. Is there in your notes? I think you could just copy and paste psql dash u capital U Postgres. psql space dash capital U.
Mm-hmm.
No, dash first, like a hyphen before
Ah,
the.
iPhone. Okay. Okay.
Yes, no, but space first before the hyphen.
Okay.
Yes. No, no,
Mm-hmm.
no, no. Immediately after the hyphen, write the U. No space. Yes.
Okay.
Okay, then now space.
Mm-hmm.
Postgres. Postgres like that. Press enter.
Password. Okay, I should create a password.
Mm, the password. Okay, okay, that's what I was asking. That was that, or what password did you set before? Just a minute.
Mm.
Of it.
Okay.
Love it. Um,
Yeah,
just type Postgres again as the default password. Let me see, as the password that they're asking you to put. Let's see.
but the first time I installed it, there was a place to put a password. Oh,
Yes, what did you put?
let me put it. But what's wrong? I cannot type.
No, you're actually typing, but it's a password, so it's not visible. So you need to
Oh,
know you're typing.
but the it's not even shifting. Not anyways. Let
Yes,
me
that's how
just
it is in the command line.
okay. But how do I even erase what I've typed? How do I know it's erased?
Just press on Linux systems. Control U should wipe everything. I'm not sure about command prompt on Windows, but let me see.
Can I start a new command prompt?
Yes, you can. You can just close this one and start a new one.
Okay, let me type in now.
Okay, yes, type it. The password you said before.
Yeah, they're saying warning. Wait, you can still see the screen now.
Yeah, I can see your screen. Console code pages. Blah, 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 blah. It's okay. So you're in. You're in. You're in. The password worked. Mm, okay. So next thing, before we even talk about this. Oh, I see. I see. I see. I mean, sorry. I'm looking at something else. Okay. So before we even talk about this, let's talk about PostgreSQL. So we said PostgreSQL is a relational database management system, right? It's a software that you use to interact with your database, in this case, your relational database. Now, in the notes, you see that it says connecting to PostgreSQL database server. Now, we talked about what a server is in the beginning, right? And I think
Mm,
yesterday, while trying to even talk about distributed systems, I talked a little bit about the client server architecture. That's how communication happens on the web, on the internet. Your clients, you the clients use it, you you use your client, which is a browser, to make a request to a server, right? And then that server gets the request and gives you an appropriate response. Now, a server, we said, is not only hardware but also software, right? Not only a computer but also software that is just there for providing data, rendering services, basically. So in this case, you see here that we're talking about connecting to the PostgreSQL server. Now, this server, in this case, is also the software that takes all of your requests that you make to the database and then gives you an appropriate response. So there are two ways to connect to the server, to the PostgreSQL server. So you can either connect using pSQL or using pgadmin. So pSQL is a terminal-based utility to connect to PostgreSQL. So in simple words, it is the CLI tool. CLI is short for command line interface. So unlike pgadmin, which makes use of, by the way, it says here that pgadmin is a web-based tool, but then this web-based tool makes use of Qt something very long and very detailed. Can't explain it right now, but then makes use of Qt in order to be able to implement this web-based application as a desktop app for you to have it like that. So anyway, the desktop app pgadmin that you use to interact with PostgreSQL makes use or implements a graphical user interface. Normally, you know that an interface is only there for interaction, right? Like say your computer, the hardware that you have, the power button that is there, that is the physical interface that you use to interact with your computer. Pressing this button means I should turn it on. Pressing it again means it should go off, right? You don't care about the intrinsics, what is happening inside the computer. You're just using the interface, so it serves also as a layer of abstraction. Okay. Now, the GUI makes use of buttons, windows, icons, some visually interesting things. So you're just maybe clicking and typing a few things for you to interact with the GUI. So PG admin is what is the interface that you use, is the graphical user interface that you use to interact with the PostgreSQL server. But then what if you want to make use of the command line interface? So unlike the GUI, the CLI makes use of commands, right? Like you saw what you had there, psql dash u, pg PostgreSQL. So you're saying that okay, you want to get into psql, you want to get into PostgreSQL using psql as the user Postgres. That dash u flag specifies user. Okay. So, but then on pgadmin, I mean, you just search maybe on your window here, pgadmin open, and then you're just doing your thing, no commands. So that's the difference. So for this lesson, we're going to make use of both psql and pgadmin, just so you see. So let's go back to psql. I just wanted to give you that overview. Let's go back to your command line. Sorry.
Okay.
All right. So you see that command. Like I said, it basically means that you're launching psql or you're trying to access the PostgreSQL database server as the user Postgres. So if there were another user, let's say there was another user called Lovett, right? What are you going to write? psql dash u Lovett, right?
Yes.
Okay. So now you've put in your password and your insight. So let's run a few SQL statements. So write, don't copy and paste. I specified in the note not to copy and paste. Write it yourself. Select version. So select all in capital letters.
Select what?
Version. Version now in small letters. Then bracket open and close. Parenthesis open and close. No, no space. No space. No, yes, yes, yes. Then put a semicolon at the end. Press enter. Great. So it gives this command gives you your PostgreSQL version, right? 18.1. It's running on Windows. Compiled by this and so on. All right, let's take the next command. Select current underscore database. So use the arrow key up. No, no, wait. Go back. Clear everything. Yes, use the arrow key
Even the
up.
Postgres.
No, 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 no. You cannot
I
even
should,
clear Postgres. Just press your arrow
okay.
key.
The
Yes, so
up
it
arrow
takes you
key.
back. Yes, the up arrow key. It takes you back to the previous command, right? So now you can
No.
just wipe. Yes, it has taken you back to the previous command. It gives you back the previous command.
Oh, okay.
So
Oh,
now instead of typing all over again, you can just wipe the part that you don't need. So wipe everything, wipe version, wipe up to where the word version starts.
I should just wipe that.
Yes, backspace, backspace, backspace. Yes, then write current underscore database, parentheses, no small letters, underscore database, yes, parentheses open and close, semicolon, press enter. Okay. So you see the current database there, it's Postgres. So when you download Postgres, default user is Postgres. You set a password, right? Default database, it also comes with a default database, or at least this is one of them, called Postgres. Okay. So now let's create another user. Let's create another user called Loved, right? So write create user all in capital letters. Create space then user
Mm-hmm.
space. Write with in capital letters like with. Yes, space. Then now password capital letters still. I even forgot one part. Go back, just use your left arrow key. After user,
Mm.
no, your left arrow. Go back, use your arrow key down. Press the
I've used it.
bottom arrow key.
I'm pressing it.
Oh, it means we've lost that command. Doesn't mean like this on Linux. Anyway, you have to type again. So create user. Just
Okay.
wipe everything. Write create user. Now, when you write that create user, put a username there. Yes, create user space. Then love it. Small letters. Space. Okay, with
Capital letter.
yes, capital letters. With password, all in capital letters.
Mm.
Space. Then now in single quotes, write the password there. Maybe you can just put love it again as the password. In single quotes.
Wait. Mm.
Yes, you can put love it again as a
Small
password.
letter.
Yes, small letters. It's your password, anything you want. But something simple that you can remember.
Wait, is it? I can put my password or just love it.
You can put any password of your choice. The next time you
Mm.
want to log in, they'll ask you for this password that you're setting now.
Uh, I'm using one password for everything. Let me just put it.
That's very bad.
I don't have memory. I might have dementia. It's hereditary in my family. I don't.
Then write it somewhere. Write it somewhere, and remember that this class is being streamed. So
Oh, oh.
even if you're putting this, I mean, you've already said you use one password for everything. So at least now you have to go and change the password.
Uh, I'll just put my name.
All right. Don't forget you started it in capital with the capital L.
Okay.
So put a
I'll
semicolon.
okay.
Press enter. Nice. So you've created a new user. Okay. So write exit in small letters. Yes. So
Exit.
yes, and then press enter. Okay. Now you're back to your normal terminal. You're no longer inside PSQL, right? You've seen how that thing at the side has changed. It's no longer showing Postgres, it's showing C users PC.
Yes.
Okay, nice. So let's run the same command again to log in to access the Postgres server, but as the user love it. So what
So
will you be writing?
P SQL
Yes,
hyphen U
yes.
Postgres.
No, in this case will be love it.
Oh, love it. Oh,
So right, let's see.
hey.
Okay,
Can you
use
can you see it?
yes, I can see your screen. So I realized this. Just use the arrow key up. But the
Mm-hmm.
user loved does not exist. The user loved with small l exists, not capital L.
Oh, yeah. Okay. Yes. Okay.
So instead of wiping everything, you could like just use the arrow keys, reach that point. Anyway, press enter, it's okay.
Okay. Then I can write my password now.
Yes, which was loved with capital L. Did you
Why
write
is
it
it?
correctly? Okay,
Yes, I
database
did. But
loved does not exist. Okay, let's look at a new error. So database loved does not exist. No, no, no. Do loved come back down where you have psql dash u and then love it instead of Postgres.
yeah. Should I wipe this
Yes.
Postgres?
Yeah, just wipe the Postgres and write love it.
Capital or small?
Small. That's your username.
Yeah.
Space. Then dash D. Postgres.
Capital D.
No, small d.
Should I space the Postgres?
Yes, give a
Is it
space
one
before
word?
Postgres.
D Postgres. Is it one word?
Yes, one word. Dash D. Postgres. Yes, like that. Press and no, no, no. It's okay. It's okay. Press enter.
Oh, okay.
Enter your password again. Let's see.
Okay.
Nice. You're in. So
Okay,
you've
it worked.
yeah, it worked. So you've seen how we can use the
Okay.
psql dash u command to log in. Okay. So now, if you run these commands here again, select this statement rather, select version, select current database, you're going to get the same result. So this is just a way for you to interact with Postgres using the CLI, using psql. Now let's try using pgadmin. So open pgadmin.
What you say?
Open pgadmin. No, 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 like the GUI, come to your menu or just
Oh,
search that search bar, right? pgadmin.
it's PG, I mean.
Yes, it's opening.
What should I do?
All right. Under servers, that drop down, click it. Click on the drop down to the left of servers. That thing that is like a right arrow. Yes,
I've
click
clicked
on
it.
it.
Mhm.
Yes, now enter your password to connect to Postgres and then check that box of save password.
I've entered, then press OK.
Yes. Did you enter the right password?
Yes, I did. Let me try it again. Wow. It's
Okay.
what we put is
Just
capital letter L Velvet now.
no, 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 no. The password that you set when you were creating.
Oh, okay. Sorry.
Remember, this is for the user Postgres, not for the user Lovett.
Mm, ah, okay. Should I let me not click on this safe password stuff?
All depends on you, just so you don't have to keep entering
Okay.
it.
I'm
Nice,
in.
you're in. So under databases, click the drop down. You see under servers there's Postgres 18, then databases. So click the drop down under databases.
This login.
No, no, drop down that arrow to the left. No, no, no. Databases. You've expanded login. Expand databases. Yes. So now you see the Postgres database, right?
Yes.
So under the Postgres database, come and expand schemas. schemas. Yes, nice. So under the public schema, you will see tables, expand tables. It's showing nothing now because there's no table that we've created. But then under tables, right click and take, scroll down. Is that all?
Yeah, that's all.
There's nothing there like query tool.
If
Click
I right
on
click on,
schemas. No, right click on schemas and
I click on schemas.
yes, okay, take query tool. Okay, so write the same SQL statement, right? Select version and then column to view your semicolon, sorry, to view your PostgreSQL version. No, parenthesis open, parenthesis open and close before semicolon. Then you
Mm,
see that those play buttons up there to the right. You have one. Are you
yeah.
see? Yes. Click on the one that says execute query.
Okay.
Take continue. You see
Oh,
the result.
down here.
Yes, same thing you got in PCQL, right?
Yes.
Now run the next command. Select current database. So instead of clearing it, you guess good. You can just put it on another line.
Select current database.
Yes, current underscore database.
Is this is it okay like
Run
this?
it. Run it. Run it. Let's see the result.
Okay.
Nice. So you get Postgres. Now notice something. When you're writing in PSQL, this current database was all in small letters, right?
Yes.
Okay. But yeah, it's also working. What is the issue? It's because SQL in general is a language that is case insensitive, meaning that whether you write a statement or anything concerning it in small letters or capital letters, you're still going to get the same result. Even if you mix the case, you're still going to get the same result. But then it is good practice to always write your clauses. Clauses are these select, insert, where you're going to see all of them, right? It is good practice for you to always write it in capital letters and then the other things in smaller letters for the purpose of readability.
All right.
Okay, so love it. We've gotten an overview of how to use what was it again? PSQL and PG admin. So I have an assignment for you. The remaining part of the notes, right?
Yes.
We have to load a sample database and then work with it, do some queries with it. So that is the task I have for you. And we're going to continue with this in the next class. So if you have any challenges doing this, reach out to me. We can even still get on a call so that I help you rectify.
Wait, please just give me again the tax. What's the tax to go to the notes and
Set up the sample database that is there. Scroll down, you see it.
okay,
Working with
working with sample.
database. Yes,
Okay.
and then just follow all the instructions under until you get to the next lesson. You see, we'll be
Okay.
running some commands,
Okay.
some statements rather. So I'm saying you should do this, and if you have any difficulties, you can write to me or request. We can get on a call, and I'll help you.
Okay.
Okay, love it.
Any,
That's the end of our class. I'll see you next time. Let me give you at least a few hours to revise for evaluation tomorrow.
okay. Thank you, Miss Miriam.
You're welcome. Good night.
Good night.